Greetings, fluid mechanics enthusiasts! Engineer Leonardo here. Well, in this video, I'd like to talk about the recent video from Numberphile, which talks about Navier-Stokes equations and the Reynolds number. Sorry. Well, I noticed on this video that the guy who's talking here, he is Tom Crawford, okay? I believe he is, I don't know if he's a mathematician or a physicist, but he made some, others can be considered to be some mistakes regarding fluid flow. So let's watch this video and I'll pause and comment on my view and my knowledge of fluid mechanics. I consider it to be misconceptions, okay? So let's go.
Today we're doing Reynolds number. Famous number, named after Reynolds, talks about fluid mechanics to do with Navier-Stokes. But it's not one number, it's not like pi. It's not, no, this is like the superhero version of pi. Because pi is fixed, pi has like one superpower.
This has nothing to do with pi. Pi is a mathematical constant. Okay, it's a irrational number which is involved with mathematics. Reynolds number, it's a physical parameter, a physical variable. Okay, so well, just an observation. Let's move on.
This is Reynolds number. This guy can morph and change to be whatever value it wants. But depending on what sort of size it is, whether it's really big or really small, you get different behavior with your fluid. So it's more like a label that you give to a particular situation. Like a fluid moving in some setup, and that's like high Reynolds number. There's one thing, if you have the same fluid moving in a slightly different setup, but it's now got a low Reynolds number, it's just completely
Okay, so this is a simplification of what laminar and turbulent flow would be. So here he's actually talking laminar flows, which he relates to low Reynolds number flow, and high Reynolds number flow related to turbulent flows. But of course, here is omitting the transition to turbulence, transitional flow, in order to be more straightforward and simplify things. But that's okay.
Using your superhero from the Avengers. If it needs to be invisible, it can be invisible. If it needs to reverse time, it can reverse time. It can do whatever it wants. Starting point, Navier-Stokes equation. So these guys model the motion, the flow of every fluid.
Not quite. Navier-Stokes equations are valid for incompressible and Newtonian flow. And of course, we are not talking about relativistic purpose. We are dealing with classical mechanics here. So no, Navier-Stokes is not valid for every fluid. It only describes Newtonian fluid, which is related to Newton's law of shear stress, Newton's law of viscosity, whatever, and incompressible flow. So it's not valid on that particular form here. It's not valid for compressive flow, for non-Newtonian fluid, for highly stratified flows. In case you're dealing with highly stratified flows, you need some additional equations, but you can base on Navier-Stokes equations. So no, Navier-Stokes equation does not describe every fluid, only incompressible and Newtonian fluid. Okay, so that's his first mistake.
The laws of physics, we have mass is conserved, we have Newton's second law,
right?
Get our equation. So we start by writing this down. We talked about these guys before. We did the full sort of what everything means.
That seems about right.
The little guy, which is conservation of mass, and then you have Newton's second law. I've made another slight simplification from the standard Navier-Stokes, and I said there are no body forces. Normally there's a big plus F here, but there's a tangent. So here's the Navier-Stokes equation. Now, you want to get the Reynolds number. So we need to define what the Reynolds number is. We label it with RE, and it's going to be our density rho times a length scale L times a velocity U divided by viscosity.
Dynamic viscosity.
The Reynolds number is Navier-Stokes equation, which you explained to us before. It's serviceable things for figuring out how fluids work. What was missing in the first place?
Here, so equation 1 is nice and simple, so we actually, that guy doesn't change with the Reynolds number discussion. But equation 2, we've got like 3 things. So we've got this guy is acceleration, which is density times the change in velocity. This guy is a pressure, and then this guy is viscosity.
Okay.
Viscosity is like an internal friction, the layers of fluid sliding over one another. We've got 3 bits. And the point is, in different situations, some of these bits will be more important. Practical example is, if viscosity was important when you get a car, you could clean your car by driving really quickly, or the air would just blast off. Exactly. So if you have loads of little bits of mud all over your car and you go really fast, the air would actually wash it off, because the friction in the air would grab onto the dirt particles in your car. So viscosity doesn't matter. As we're going to see, the Reynolds number. In some situations,
actually, it matters. No, it doesn't matter if you're dealing with laminar and turbulent flow. Viscosity does play a significant role in turbulent flows.
Or equally important. But in certain situations, like the extreme cases, you can get that one of them doesn't actually matter, or one of them is so important that dominates the other two. And then you've got a nice, simpler equation we can then solve. Because we know we can't always solve that mistake. So if we can get our hands on this Reynolds number, allows us to simplify them and actually solve them and get them.
So the Reynolds number is what apportions different weightings to the different factors.
Exactly.
So I believe that's okay. This is a compressed flow, Newtonian. This is not Newtonian flow. This is actually no Newtonian flow. Here in compressive and Newtonian. In compressive and Newtonian, in fact. In compressive and Newtonian flow. And again, in compressive and Newtonian. Also.
You can either have a really big Reynolds number or really small.
The video showed also blood flow is not a Newtonian fluid. Blood is more like, if I'm not mistaken, pseudo-plastic, or no, sorry, it's a dilatant type of fluid, so it's actually a non-Newtonian fluid. But let's move on.
Sort of the standard thing we do in math is consider if it's really big or it's really small.
And just so I've got some idea of what numbers we're talking about like billions and negative numbers, like so
the Reynolds number has to be positive, because it's a density times a length times a velocity over a distance. These are positive physical things you can measure. And you plug those values in, you'll get the number. So it can be as small as sort of, you move back down towards 0, can't be 0, it's just above 0, or it can go as big as you want. Generally, we're talking sort of 10 to 1,000 most everyday situation. If it's over 1,000, it's turbulent. The turbulence is this chaotic, crazy motion.
Here, whether or not a fluid flow is turbulent, it depends on the flow you're considering. Again, a Reynolds number of about 1,000 can be laminar flow for certain types of fluid. Okay, so let's say you can have laminar flow like Reynolds number at 100, but at Reynolds number equal 100, you can have actually a turbulent flow for other type of flow. An example would be channel flow and pipe flow, right? So you have different laminar range of Reynolds number for these types of flows, and different Reynolds that governs the transition to turbulence on these flows. Okay, so this you can say that is a general Reynolds number at which we have a fully developed turbulent flow. But let's move on.
We have two cases of Reynolds number. We've got big Reynolds number, so we say it's not just greater than 1, it's much greater than 1.
Okay.
1,000 above turbulence. And your equations, so we've got rid now of all of the sort of these guys, like the mu and the rho, they're in the Reynolds number now, so they're gone. And so what that means is you can start to compare your terms and you end up with this guy, 1 over Reynolds. So if we compare this one.
Okay, so this equation is clearly wrong, right? So we made the Navier-Stokes dimensionless. So now that instead of having the viscosity here, we have the Reynolds number. Actually, the equation that it's written here by his hand, it's right. Okay, so here we have 1 divided by the Reynolds number, which multiplies the Laplacian, the viscosity term. But here it's wrong, okay? We don't have this dynamic viscosity term here. It's only 1 divided by Reynolds. So this equation is wrong, okay?
We have
here it's correct, the dimensional form of Navier-Stokes, and here it would be the dimensionless form, but without this dynamic viscosity. Well, let's move on.
We've still got acceleration, we've still got pressure,
right?
we've got viscosity. Now we've sort of got rid of all the other little bits.
It's correct here.
Now we can compare it.
It's correct.
Because by introducing the Reynolds number, what we've done is we've non-dimensionalized the system, which means get rid of the unit. If I say
right.
I have 10 apples and I have 9 bananas, then if we consider apples, I have more fruit with my 10 apples than I do with my 9 bananas. But with my 9 bananas, I have more potassium than I do with my apples. The units matter. It depends. You can't say I have more apples than bananas. It depends whether I'm talking about fruit or potassium. The units are important. So now, by introducing the Reynolds number, what we've done is a non-dimensionalization, and we've got rid of it. So now we can compare acceleration, pressure, and viscosity. 3 very different things with different units, but now they have no unit. If the number associated with the acceleration term is bigger than the number associated with pressure, that means acceleration is bigger than pressure. It makes sense to compare them because they have no unit. This is the power of the Reynolds number, really.
Does the Reynolds number itself have units then?
The Reynolds number does not have units. The Reynolds number is just a number, and we can actually
correct.
See that. So the Reynolds number itself is density times length times speed divided by viscosity. So think about the units.
That's a real hot pot for units.
It is. So density, that's going to be kilograms per meter cubed in 3D. So we use the square bracket notation for the units. For our length, well, that's just in meters. Our velocity, u, that's in meters per second. And then our viscosity, this one is possibly less well known, but this guy is kilograms per meter per second. And now, if we put them all together in the Reynolds number formula, we get the RE, the units. So on the top, we've got a density, so it's a kg, that's 3. Then we've got a length, that's an m. Then we've got a speed, that's 1. And then we divide through by viscosity. Now, hopefully, things like kilograms cancel, meters minus 3 gives us meters minus 1, cancels, etc. The Reynolds number has.
Brilliant.
Okay.
It's just a number. That's why it's called Reynolds number. It's just a number. It's why we can think about what happens when it's big. Yeah. So now the Reynolds number is really big. We've got acceleration equals pressure plus 1 over a really big number times viscosity. So 1 divided by a really big number is really small. What that's telling us is that guy doesn't matter. So in the situation, really large Reynolds number
actually matter.
could be very, very light,
Okay.
very, very high density, very, very long fluids, or very, very fast. So
wait, what the hell? Sorry for the vocabulary, but what the hell is a long fluid? It's a long flow. Okay, L is the characteristic length of the flow, not the fluid. It's a flow characteristic. Reynolds number are flow characteristics, not fluid characteristics. Okay, we have to distinguish one from the other. So what would be a characteristic length of the fluid? In the case of pipe flow, it would be the diameter of the pipe. In the case of the channel, it will be the hydraulic radius, for example. In the case around, let's say, a cylinder, it would be its diameter and so on. So it's a property of the flow, not the fluid.
You can make this thing big however you have to. This viscosity doesn't matter. You're driving your car, you're going really, really fast.
It actually matters. A turbulent flow without viscosity is not the same as let's say, a frictionless flow, a medial fluid flow. Okay. So when you disregard the viscosity term, you arrive at the Euler equations, which don't describe as fluid as well as the Navier-Stokes equation. Other equations have several problems, like the Dalembert paradox. It arrives at certain situations where it would have infinite drag and some other problems. But let's move on.
That's why the viscosity there doesn't clean the dirt from your car. Because you're in this large Reynolds number, and your equations say viscosity doesn't matter.
It matters.
The Reynolds number is now really, really small. We say it's much less than one. It's not just a smaller one, it's much less. And so what happens now with our equations?
You have laminar flow.
If you are non-dimensionalization the same way as before, now we've got Reynolds number times acceleration equals a pressure term plus the viscosity.
Okay. Why didn't he multiply the pressure term by the Reynolds number? Because he multiplied the whole equation by the Reynolds number. That doesn't make any sense. It's another mistake in writing these equations. Right?
So now it's slightly different to what we have. So we've got Reynolds number is the number times acceleration is pressure plus viscosity. You might be wondering,
where is the Reynolds number?
Here, why is it on acceleration? And before we had it over on viscosity. Now we have a small Reynolds number. So the small Reynolds number flow, you sort of know with experiments to say that the pressure term is actually balanced by viscosity, whereas in the big Reynolds number case, the pressure term is balanced by the acceleration. So that there is some slight difference in how you non-dimensionalize, but it still works in the same way. It still has units of pressure. You just have this choice between how to balance your pressure. So when the Reynolds number is small, you have this guy. With Reynolds times acceleration is pressure.
He actually is talking more in the sense of Bernoulli equation. So if you remember Bernoulli equation, you have the velocity term and the pressure term. So in high Reynolds number, you arrive at the other equations, and then you can derive the Bernoulli equation. So there you can have the velocity. It's a balance of energy where you have velocity and pressure. But for a laminar flow, it doesn't work really like that.
But the Reynolds number is really small. Now I've got a tiny number times acceleration. So acceleration.
What about the pressure?
Because Reynolds number is really small. So that now goes. So this is the term that doesn't matter in this small Reynolds number.
How come it doesn't matter? You can actually have a steady laminar flow. I have one video about that, where I derive an equation for a steady co-ed flow, on which co-ed flow is a type of laminar flow.
We've got pressure and viscosity. Our governing equation is just pressure gradient. My favorite thing, I'm going to say it all in blue, is getting this result, because we no longer have time in our equation.
Only if you consider that your flow is fully developed. You always have time in your equation. You can disregard time and consider that your flow is fully developed. You have a steady flow. You are not studying the initial developing of a flow, the unsteady part of a flow. But whatever.
We've started with Navier-Stokes, which we know are true. Mass is conserved, Newton's second law. That's a given. Then we've looked at small Reynolds number. It turns out that in that situation, time vanishes from our equation.
Because the only thing bringing time to the table was acceleration.
No.
Exactly. The only possible t in our equation is an acceleration. So now that's gone. It doesn't matter. I mean, it's still there. It doesn't matter. Everything else is bigger than it, so they dominate.
Not quite. You're making the same mistake that you made when you talk about high Reynolds number. So,
is that when you have a small Reynolds number, time doesn't matter. So if you go forward in time, and then you do the exact same
that doesn't
thing,
even make sense.
it has to be the same thing, because the pressure and the velocity have to still be the same. If you go forwards and then you go backwards, you can get back later. You can literally time travel. You can time travel in a fluid.
What the?
Because the Reynolds number is small, time divided. So how do we get the Reynolds number? We've got density times length times velocity divided by viscosity. Make viscosity big.
Okay, that's correct.
A large viscosity means they're very thick. If the fluid, let's take corn syrup, sugar syrup, your favorite type of syrup. It's very thick, it's very
Syrup
thick,
is no Newtonian fluid. Damn it.
Let's see if we can do an experiment and get the same thing as we go forward in time and then backwards in time. The equations say here's a cylindrical container filled.
Only if you know how to apply the equations. Instead, they won't work properly. Okay?
Sugar syrup, we're going to add 3 drops of food coloring. And then if we slowly turn this stirrer and mix the fluids together, we go forwards in time. So we'll do several rotations.
That's nice. Okay, here we have a laminar and unsteady flow, and so you can see the flow is changing with time, so time matters. What is wrong with this guy? That's actually a very nice experiment.
And then stop, and as you can see, the blobs of food dye have mixed together, as you might expect. Now, if we do the exact same thing in reverse, with the same speed, the same pressure, everything the same, but we reverse the direction of our stirrer, we're going backwards in time.
You're not going backwards in time.
And as you can see, it's magic. Voila! We have gone back to the very beginning. We have mixed them together forwards in time, and then gone backwards in the exact same way, and returned to our original.
That happens because we're dealing with laminar flow. So laminar flow, to our current tools in mathematics and physics, is a deterministic type of flow. Knowing the initial state, we can know the end states of that using the equations of that type of flow, because it's not a chaotic type of motion. Different than turbulent flow, in which the flow is by definition chaotic, so we are uncertain regarding its final state, knowing its initial state. So that's the basic difference between laminar and turbulent flow. Laminar flow, we can it's easier to reproduce in laboratory experiments and arrive at the same results because of its nature, of the nature of laminar flow, which is not as a turbulent flow. So we will try to reproduce a turbulent flow in different laboratories, say laboratory A and laboratory B, and measure the velocity on the same position on the 2 experiments. You would obtain different results even if you have the same initial conditions for these flows. Okay, so that's the difference between laminar and turbulent flow. It has nothing to do with time doesn't not mattering or being not important on this type of flow. Okay.
And this works because time is not in our government.
It is governing the equations.
Without this knowledge, we wouldn't know to even try this experiment. We wouldn't know to pick a really sticky fluid and see this awesome thing happen. But it is explained by the fact that time disappears.
It doesn't.
What's the bonus or the cool thing about a really big Reynolds number?
Big Reynolds number. A big Reynolds number just means super turbulent flow. So
in general,
any kind of aerodynamic flow around a Formula 1 car, flow around a jet, that's large. And the issue with large Reynolds number flight is turbulence. And turbulence we don't understand. Turbulence is one of the reasons
we sort of understand many of its features, but it's very complex naturally.
We don't understand Navier-Stokes. Possibly one of the ways of getting that really.
We understand Navier-Stokes physically and in its applicability in engineering, okay, but we don't understand it, let's say, mathematically. We don't understand the main mathematical features.
Large Reynolds number flows, turbulence, very, very difficult. But fortunately, small Reynolds number flows make a bit more sense. And the intricate math, or the key bit of the math, is that when you have the small Reynolds number, as well as losing time, you use time because you lose the acceleration.
You don't lose anything.
Is non-linear. So what that means is that's the difficulty of Navier-Stokes. The reason Navier-Stokes are such a hard set of equations to solve is because they're non-linear. So that means if you have one solution,
right,
solution A, and you have a second solution B, for a linear equation, A plus B will also satisfy. But Navier-Stokes is non-linear, so when you A plus B, you don't get a solution. And that's how we generally solve difficult partial differential equations. Difficult differential equations in general. We find one solution, find one that's similar to it, and keep adding them all together, and you get all of the solutions. But we can't do it because Navier-Stokes is linear. But it's only non-linear with big Reynolds number. If we take small Reynolds number, we've lost acceleration, we've lost time, we've lost non-linearity, and then we can actually solve it and get interesting solutions.
Unfortunately, that's not a very practical thing. That doesn't happen very often in the real world.
It doesn't, no. So Reynolds numbers, generally in the real world,
solve them numerically. CFD.
Take the wind, the water in a river, in an ocean. Most of our interactions with fluids are turbulent or are at least 100 points on the Reynolds number scale. This kind of thing, getting rid of the nonlinear bit, getting rid of time, like you need much less of that. You don't really see that in most of our work. You run on a tiny little bacteria scale. You think about it, going on a really small cell, like individual cell scale. You might start to get small enough length scale with a Reynolds number. But in our world, unfortunately, we live in a turbulent world.
Most of the time. Okay, so hope you like this video. Don't forget to like, subscribe, and comment, and share this video with others. Don't forget to subscribe. Okay, see you next time. Bye.